Good afternoon, everybody, and welcome to today's edition of MetalCon Live, What Makes Rainscreen Walls Work? And today's session is being presented in association with RAINA, the Rainscreen Industry in North America Association. I hope I got that right, Todd. Please correct me if I didn't.
No worries. Close enough. Rainscreen Association in North America. Thanks, Kayla.
Thank you. Okay. And we are, of course, joined by Todd Kimmel, who is a wonderful speaker coming in from Rockwell and the RAINA Association. RAINA is a huge organization and a new organization in North America. They're a fantastic group of individuals that are helping to bring the world of rain screens to light across all buildings in North America. If you have any questions about rain screens, how you can get involved in the association, or what you can do going forward with regards to rain screens, you can find out more at their website at rainscreenassociation.org. We hope you'll mark your calendars for our next MetalCon Live happening on Wednesday, December 6th. And that session is Air Barriers for Whole Buildings, which is being presented by the Air Barrier Association of America, or in America. And that will be presented by Laverne Dalgleish, who is a seasoned speaker as well. Following this session, you will be receiving a form at the end where you'll be able to receive your certificates of attendance. And if you are an AIA member, where you'll be able to receive your AIA credit as well. All questions will be held until there is an appropriate moment for a break in the presentation, but please submit all questions that you may have through the chat box at any point in time. If you can only find the Q&A, we'll find your questions there as well. And if you have any further questions, run into any technical issues or anything of that sort, you can always contact me, MetalCon Live, in the chat, and I'll be able to help you from there. Without further ado, I'm going to hand this over to Todd. Todd, go ahead and take it away.
Thanks, Kaylin. Let's see. Can everyone see my screen? Caitlin, can you see my screen now?
Yes, I can.
Awesome. All right, well, first of all, I want to thank MetalCon for inviting the Rainscreen Association in North America to come in and speak and present today on what makes Rainscreen walls work. This was a program actually we recently presented at the MetalCon conference in Las Vegas just a few weeks ago, and there was some great feedback and some great attendance. And just participation activity with our booth and certainly with the programs that we were presenting. So yeah, enthusiastic to carry on this kind of charge and this alignment with MetalCon to kind of provide this great education. So this is me. As Kaylin mentioned, I am a co-founder of the Rainscreen Association. I'm the current chairperson as well. I've spent a number of years working in the exterior envelope building products industry and kind of the contractor side of the world as well. So I have a lot of insight and integration with not just claddings, but with membranes and with insulation as well. I currently work at Rockwell, and I'm sure many of our attendees here are familiar with that product as well. So before I dive in on today's program, I just want to kind of identify a little bit, about RAINA, who we are, what we're doing, and I would assume many people on this call are familiar with the term rain screen and maybe confused sometimes in terms of what the definition is, and maybe even now why do we have an association dedicated to rain screens. And so, I'm not going to assume that everyone on this call likes, beautiful BLT sandwiches, but I think we can all agree, similar to the food that we eat, all the ingredients make a difference, and kind of how they come together make a difference in terms of the outcomes. And the same thing with our building envelopes, right? We have a lot of products that we need to integrate for performance, not just the aesthetic, but also the control layers within our walls, whether or not we're managing moisture or air or thermal or vapor migration, and how that kind of comes together with our structure, and what else we need to kind of think about with acoustics and with fire performance. And so we want this sandwich to work well, and many of the rain screen manufacturers out there, or cladding manufacturers out there, may or may not provide systems or components or the water resistant barriers. And so we wanted to come together as an association to minimize any confusion, to come through with kind of consensus-based vision on terms and definitions, on performance expectations. But we really understood that, hey, this is not just about individual product manufacturers of various claddings or membranes or insulations. This is a trade association that we want to kind of support the growth of this type of an assembly within the industry. So many of our members are also architects, engineers, consultants, other trade associations in similar spaces, obviously the contractors, testing agencies. And so where we see success is at the center of this complex Venn diagram, where we're bringing everybody in and really kind of creating the best program to move forward with Rainscreen. And so today's program is going to be kind of the basics and kind of explaining what a Rainscreen is and how it works and how all those parts and pieces come together. So we will certainly talk about claddings. We'll talk about cavity, airflow, ventilation, the term ventilation versus vented. We'll get into water resistant barriers and attachment strategies, all these things that you see on this list. And so what I want to start with, and I think what the association is very proud of, one of the first items that we addressed, particularly our definitions committee, was the term Rainscreen. Is it one word or is it two words? And what is that definition? And so what we've agreed to is that a Rainscreen, one word, is an assembly applied to an exterior wall which consists of, at a minimum, an outer layer, an inner layer, and a cavity between them that's sufficient for the passive removal of both liquid water and water vapor. And so you can see here, this is that minimum, the outer layer, which is made up of a cladding, the inner layer, which in this case is made up of a water-resistant barrier against the sheathing, and very simply put, a cavity that's between them that's, again, sufficient for the passive removal of both liquid water and water vapor. And so it's not a product. Let's see if I can get in. Hold on here. And it's not building type specific. I apologize. So, when we look at these three different wall assemblies, these are all Rainscreen assemblies, right? And it doesn't make a difference if it's wood-based construction, metal frame construction, or mass wall construction. All kind of integrating these systems would be defined as a Rainscreen. And so almost any cladding and any backup wall that's separated by that cavity that's both drained and either vented or ventilated would service as a Rainscreen. And it's not a new concept. These are some images from 1962. This was C.K. Garden. This was a publication in the Canadian Building Digest. And you can see the identification, whether or not we're talking residential shingled wall that kind of necessitated having an airspace and an air barrier, or these cavity brick walls, which kind of included ventilation, the weep holes, brick veneers doing the same. We see metal panels where a vented batten is really critical for kind of managing the moisture within those assemblies. Even in concrete panels, we see different types of mechanisms to escape moisture with the terms of either venting or ventilation. And even when we look at window walls or curtain walls, certainly in the mullions, there's very similar building science around how we're managing moisture within those connections. It's not the only way to manage moisture within your walls, right? There's different ways to do that. This is just kind of an overarching chart, kind of explaining how moisture can be managed in walls. And we'll start on the left side where we see the term perfect barrier, and it's not to make make this seem like this is a perfect way to address things. A perfect barrier wall system is really meaning that it's a single layer system where you're managing moisture and air and vapor and sometimes thermal in a single layer, and there's not any levels of redundancy, right? So those wall assemblies need to be built perfect. And as we can, all imagine, being perfect is not always easy. And if it isn't perfect, there's not layers of, again, redundancy to help manage moisture. So we'll get into the kind of examples of what that looks like in just a minute, but we're talking a lot about face sealed systems or concealed barrier systems. On the right-hand side of this chart, we see the term imperfect barrier. And again, not to say that these are faulty systems, but these are systems that recognize that moisture is likely going to get in, that it's hard to be perfect. And so what are those mechanisms that we can implement to manage that moisture if it does get by that kind of first layer of defense? And in mass or storage walls, right, like let's say brick or rubble, or things like that, those materials are moisture tolerant. They might take on moisture, but then they can evacuate moisture without jeopardizing the integrity of that material or that assembly or that structure. Other ways to do it is with drained or screen walls, right? And that's where we start to see, okay, the outer layer is not perfect, moisture gets in. How do we manage that moisture once it gets behind the cladding? And we see terms like vented, ventilated, or sometimes ventilated, pressure moderated, or ideally pressure equalized systems. And that's kind of where the Rainscreen realm fits into play. All right, so we look at these approaches on the left-hand side again. The perfect barrier wall is an exclusionary wall. It needs to be done perfectly. When we talk about structural glazing, if we look at architectural precast or insulated metal panels, or even some of these, kind of face seal eave systems, they all have to be done perfect. And we all know that these systems also require sealants in terms of making connections effective. And those sealants will wear down over time. They need to be remediated. They need to be kind of addressed periodically. Otherwise, moisture gets in and you start to have problems. On the right-hand side, you see the examples of these imperfect barrier systems. And I mentioned mass and storage walls. We can also look at some of these drainage type systems on here. Masonry veneer introduces this drainage and ventilation technique. We see a tremendous amount of again, panel cladding systems, these Rainscreen systems that you can see here in the lower right. Again, managing moisture that gets behind the cladding, recognizing that moisture will get behind the cladding. And so how do Rainscreen walls get wet, and then how do they dry out? So with any wall, really, you can see here on the left is the wetting mechanisms on walls, right? Liquid water or precipitation can hit the wall and get in for sure. But we also see moisture moving in different ways, right? Water vapor movement, vapor diffusion through our assemblies from higher vapor pressure to lower vapor pressure. Typically, we're moving from hot to cold in that case, which can, switch around depending on where we're at in the United States or wherever, right? Dual climates like the Northeast, we have hot, humid summers, we have cold, dry winters, and so vapor will migrate through our walls in different ways throughout the course of the year. We also have built-in moisture within the construction, right? These projects that are built out of wood or concrete, right? These materials will be wet or certainly can be wet during the process of construction. And then when that construction is complete, that moisture still needs to evacuate out of those materials. So we have to kind of take into account the moisture from that perspective. We also see groundwater, but we're not going to be as concerned about that here today when it kind of is concerning Rainscreen walls. And then on the right-hand side, we look at how do walls dry out. So firstly, you have evaporation. So if moisture hits walls on either the interior or the exterior surface, that moisture can evaporate to the air. We still see that diffusion, right? So again, if moisture is trapped in our assemblies, vapor diffusion can allow for drying either inward or outward, depending on the movement of the vapor pressure in the moment. Drainage is certainly a key way to get rid of liquid water. We see multiple pathways of drainage within this assembly, both at the face of the cladding, at the rear side of the cladding, maybe even over the sheathing. And then we also have ventilation, right? Drying by air exchange, which is really key, and we'll get into that in the slides ahead. But that means air movement that's happening within the cavity from multiple openings behind the cladding, right? And that allows for, again, more rapid drying of any incidental moisture that gets into or is trying to get out of our walls. And again, so a Rainscreen wall at a minimum has an outer layer, which here is traditionally the cladding. We have a cavity behind it. We have the inner layer, which we often see as the water resistant barrier in this assembly. And then you have flashings and drainage openings. You also obviously need to kind of have a backup structure for this attached to, and that can be a variety of things. But when we look at modern wall construction, Rainscreen could also include a few other things. Oftentimes, we need exterior insulation, continuous insulation within our assemblies. And so that can be incorporated within that cavity space without compromising, let's say, the open cavity. We'll talk about that as well. But that, insulation, which could be 1, 2, 3, 5, 10 inches, also kind of makes it a little bit more challenging in terms of how are we going to, support our cladding. And so we need to have support structure, kind of extending off the wall to support that cladding further off. That's going to be part of that assembly. Energy codes are also now requiring airtight or improved air tightness within our assemblies. And a water resistant barrier, as we'll see, is a really great place to start for air tightness as well. So those membranes might sometimes just be serving as a water resistant barrier, but they could also be part of an air barrier system And so that is also an integral part of this assembly if that's how we're designing these walls, not to mention vapor control, right? So these membranes and even the insulations and the claddings can all have an impact on vapor migration, vapor openness, or vapor closeness in terms of managing vapor as it moves through the wall. So understanding that those factors is really important. There's a number of loads that these assemblies need to kind of consider and be designed around. Structural loads for sure, whether or not we're talking about dead loads and live loads from gravity or wind or seismic. Some cases we'll see blast or cyclic loading that's required based on kind of the structure and what the expectations of movement are. So those considerations, like any cladding, need to be taken into account. The environmental loads as well, like what is the exterior environment doing within these assemblies, right? Obviously, we're talking about rain in many of these assemblies, but we could be talking about snow or ice. We could see huge temperature shifts and the impact of that on the claddings and on the systems. UV, certainly, right? There's a lot of exposure here. When we talk about open joint claddings that allow for UV to bypass the cladding layer, and possibly hit not just the insulation, but maybe even the water resistive or the air barriers. Those are things that we need to understand and design around. Combustion loading is really, really critical, right? We all understand the need to have fire-safe buildings with fire-safe materials, whether or not that's cladding or insulation or membranes. And then when we combine these products together, how are those going to work in kind of assembly tests? So understanding that is really critical as well. And so again, some examples here. And we're kind of outlining our outer layer, our inner layer, and that cavity between them. But these are all types of rain screens, whether or not we're looking at wood-based, let's say residential and multifamily construction here on the left, or if we're looking at more commercial grade type assemblies of either metal framing or mass walls here on the right. These are all examples of rain screens. And so let's get more visual. Again, this wood-based construction that we see here on the left, we can see that the extrusions, or let's say the furring strips, are applied to the exterior, which will eventually house the cladding. In the middle, we can see steel girt or hat channels framing to kind of support the cladding. Up above, we see kind of clip and rail type assemblies, which we'll talk about in a little bit. Down below, we see some continuous hat channels over the insulation that's eventually going to support that cladding. And then we see on the right a different form of rain screen, but it kind of serves the same purpose. These might be for moisture absorptive claddings, such as stucco or stone veneers. But we see, these entangled mesh or dimple sheet products that, again, provide a drainage and a ventilation space behind the cladding, but allow for kind of a continuous applied cladding to the face of that. And these are quite common in the residential market and sometimes the multifamily market. It's just a different strategy of creating that drainage and ventilation space. And so I mentioned before, lots of claddings can be rain screen, right? It's the exterior finish, it's the water shedding layer that's exposed to the environment. But we see tons of different materials serving as this. So the cladding itself does not make the rain screen assembly, but it is part of the rain screen assembly. And we see, plate steel, plate aluminum, aluminum composite metal, different, certainly speaking to the metalcom crowd, there's a tremendous amount of metal that can be used, copper, other types of products for sure. But we also see fiber cements, we see terracotta, we see brick, we see stone, we see high pressure laminates, we see other types of polymers, we see porcelains, right? There's a tremendous amount of claddings that can be assembled as a rain screen within the wall. And those assemblies also will, or those claddings will also include kind of the joint treatments. Some of them will have integral lapping kind of conditions. Some of them will include open joints or splines. They might have flashings, different types of trims and accessories. And so, different claddings can have a different degree of openness. Some claddings are perforated. Some claddings, require levels of movement at the joint. So having an open joint, either vertically or horizontally, is going to be important for the thermal movement of those products. And that degree of openness kind of, again, impacts the water that can get in, the ultraviolet light that can get in, maybe pests and insects that can come in. So understanding that, we need to design around that and understand kind of what the impact is. And so, any cladding, right, is a different type of vinyl siding, so to speak. But yes, right. I mean, these provided it's allowing that drainage and ventilation, has an outer layer and inner layer. This, in theory, can serve as a rain screen. So, rain screens are used in heavy water loading locations. They are used to really manage that moisture effectively, recognizing that it's hard to be perfect, and we want to come and have redundancy and levels of strategies to manage the moisture that's hitting the wall. Right. And those benefits go beyond just the rain control. We talk about ventilation. We talk about allowing those assemblies to dry out effectively. And we might not be just drying out liquid water. We might be trying to, dry out any sort of condensate moisture that occurred within the assembly if moisture was trying to escape from the wall. We also want to recognize that, if we're thinking about using vapor tight claddings, if they are installed as rain screens with openings, that vapor is going to bypass that cladding and it might condense, and we want to manage that as well. Right. So we see, rain screens in all these kind of high purple regions quite often, but we also see them used in hot, dry climates, right? In terms of managing the thermal impact. And in a lot of those kind of hot, dry climates, when it does rain, for those like 10 minutes a year, it rains pretty hard, right? So it's also really important to have those considerations in those kind of neck of the woods. And I think it's important to understand, right? So for a leak to exist in a building, right, we need three things to happen all at once, right? We need that water to hit the surface. We need a force. We need that wind or that momentum or the capillary suction or the negative pressure acting on the wall. And we need an opening, right? If one of those things is missing, we're not going to get a leak. And so, one of the mechanisms that, we can kind of go forward with our cladding systems is looking at ways to reduce the impact of one of those three or multiple of those three items. And so lapped or kind of well-jointed claddings that are properly shingled, really reduce the amount of moisture, if they're done effectively, from getting behind the cladding to begin with, right? And this is done quite often. We see this often on residential buildings for sure, also sometimes on commercial buildings. But it takes a little bit onus off the perfection of what's behind the cladding when you're, really doing a good job of installing claddings that keep that water from getting back there. Some of these panel claddings are kind of, not lapped or kind of adjacent, and they might have, minimal or small joints that are tried to be closed, but maybe a little bit of more water gets back there. So we need to start thinking a little bit more closely on how we're going to manage that moisture behind. And then we also see a tremendous amount of open joint or perforated claddings, right? And, there's not, necessarily failure that occurs here. It's just understanding that, okay, well, we have open joint, we have more moisture getting behind the cladding. The attention to detail on what's going behind the cladding is now a little bit more important. One of our claddings like this, right, where, these are successfully installed rain screen systems, and certainly they're more open than what we would traditionally see, but that's okay. So, open joints, right? We're allowing more water and UV in, and we got to manage that, right? So here on the left, we see kind of more of a closed joint type system. The next one, maybe we have open joints, but we have concealed hat channels that can help manage the moisture and limit the impact behind the assembly. In some cases, we have wider open joints where we're letting more moisture in. Here we're seeing an example with continuous insulation, which actually offers another line of defense for moisture. And maybe we have perforated claddings where we have lots of holes in our claddings. And again, just kind of showing from the minimal amount of moisture to the most amount of moisture that we might see in a wall. All right, so when we look at the cavity and understand that airspace and the gap, right, what is it trying to do, and what are the minimums or maybe what are the maximums we want with those gaps? When we talk about capillary action, right, and capillary action is kind of how moisture can move in things, without external forces, right? If we were to put, a sheet of paper into water, we can see that water starts to travel up the fibers of that product. I'm sorry, of that paper, right? And that can happen in walls too. And so we want to stop that capillary action in the penetrations that we might have on our WRB. And so having a gap of just over 0.1 millimeters is actually enough to really stop the impact of that capillary action. We want to stop the water, the transfer, the bridging across from the outer layer to the inner layer. So when we look at a minimum joint size or cavity size to stop that transfer, that bridging of, let's say, just a single water droplet, really 3 millimeters is that minimum, right? To kind of minimize that impact of that water bypassing or kind of transferring through that cavity. Excuse me. So when we look at drainage and kind of the ability for kind of gravity to kind of bring that moisture down, we really don't need that much, right? Just under a millimeter is ample for drainage to occur effectively within these assemblies. But then when we want to incorporate ventilation, that air movement to kind of get rid of the vapor or trapped vapor within those assemblies, now we're again back up to over 3 millimeters. When we talk about fire and smoke, we'll get into that in a little bit, but I should say smoke propagation. If you're over 25 millimeters in depth, that starts to have an impact on a lot more airflow and potential for smoke and fire to kind of move within an assembly. So when we look at not a minimum, but maybe I don't want to call it a maximum, but where that kind of flame and smoke starts to move more rapidly is when we get above 25 millimeters, which again is a little bit over an inch. So Canadian code, if we're looking at kind of Canadian applications, 10 millimeters is usually the minimum that you'd see in a rain screen. But traditionally and oftentimes you see anywhere between 3/4 of an inch to an inch within those assemblies. And also the degree of compartmentalization can also impact the kind of pressure moderation or the equalization that you might see. And we'll talk about that in a little bit in terms of trying to minimize the air pressures that are acting up against the wall by moderating it through the joinery. All right, so impact of the cavity and kind of the drainage and airflow side of it. So if you have no gap, right, there's no drainage or airflow possible, this may as well be an exclusionary wall where we have to be perfect on the outside. If moisture gets in, there's really no way to really manage it. Smaller gaps, again, you don't need much to get some drainage working in your benefit, up to about 1/8 of an inch. But you're really not leveraging the benefit of airflow and the movement of that airflow to help more rapidly dry out those assemblies. When you're up around 1/2 an inch, then not only are you getting the full drainage, but you're also getting some decent airflow potential to kind of evacuate the trap moisture or certainly the water vapor that might get behind the cladding or come out from inside the wall to behind the cladding. As we move up over 3/4 of an inch, that kind of drainage only improves, as well as the airflow potential to kind of help rapidly dry those assemblies out. All right, so creating that gap, right? There's obviously lots of different assemblies. We talked about this already a little bit. If we're not using continuous insulation, for the claddings on the left-hand side, just a traditional hat channel can really provide that drainage and ventilation space. When we look at masonry walls, kind of extending brick off walls, the kind of clips that we see here are kind of offering that benefit. On the right-hand side, as we mentioned, these engineered drainage or kind of venting composite materials do a really good job of providing that drainage and ventilation for these continuous kind of moisture absorptive claddings. So drainage and airflow considerations within these systems. So here on the left, we're looking at vertically oriented cladding supports, right? So the cladding is attached back to the structure using an extrusion that's running vertical up the wall. And you can see here that, these vertically oriented supports allow for that gravity to, promote drainage, and you have an opening at the bottom of the system to allow moisture out. Where we oftentimes see, challenges when installing, a rain screen system is if somebody puts a horizontal component, and maybe they're doing that because the cladding needs to attach to a structural, framing, and the cladding attachment might not be 16 inches on center or 24 inches on center so that you can attach directly back to the stud within a metal frame wall. So what do? They put the hat channel in horizontally. And so that's great because now we can attach our cladding wherever it needs to be attached. However, we might be forgetting that, we need some levels of drainage and potentially ventilation. But in this case, we're seeing that water, if it gets behind the cladding, now might pool on the backside of the cladding over the hat channel. And it's really blocking that drainage or that airflow. And we need to kind of avoid those scenarios. And we can avoid them in different ways. If our cladding, for instance, is a profiled cladding, like an undulating kind of corrugated type product, that hat channel running horizontally might not be a big deal because the cladding itself has mechanisms for the water and the airflow to get behind it in front of that horizontal component. And we're seeing more of these types of assemblies where now, instead of having, even if you didn't have a profiled cladding and you had a compact cladding, if you had perforations built into your hat channel, that certainly will allow for that drainage that you're effectively trying to use. And so now we'll ask, let's spot the airflow and the drainage on these systems. And so you see here on the left, on the top, obviously we have these kind of vertical rails attached to clips. On the bottom, we have these hat channels outboard of the insulation, providing that drainage and ventilation space. This one might be more visually challenging to see. So what we're looking at is an inside corner of a wall. You can see the insulation in the corner kind of on a return wall, and that cladding is a corrugated kind of accordion metal. And so the drainage and ventilation space there is actually behind that profile. And now here on the right, I'm going to end this with a question mark, because if you look closely, it certainly seems like the insulation is right to the face of that cladding support mechanism. So I question whether or not there is ample drainage within this system. Maybe there's some weeps or shims at that horizontal to extend the cladding proud of the insulation. But this is something where we'd start to ask the question, do we have enough drainage within those assemblies? All right, so now we're going to kind of hopefully demystify the vent versus venting comment, right? So when we look at these systems, you're looking at the one here on the left, the opening is only at the bottom of the cladding, right? The flashing that goes over the cladding panel below it seems to be sealed up. And so ultimately, we're not getting that true ventilation of multiple openings in the cladding to promote that, more active airflow. And we're using, the ventilation, or I'm sorry, the venting to allow for drainage and certainly a little bit of airflow, but not a tremendous amount. When we talk about being ventilated, right, we want an opening at the bottom and an opening at the top of the cladding, right? And that really helps to promote the higher airflow rates and to kind of evaporate and kind of get that water and that vapor evacuated much more quickly. When we look at fire, right, and we'll talk a little bit more about that in a bit, but if there's no gap, right, I mean, oxygen feeds fire. So if there's no gap or any sort of ventilation, you're not going to have the ability for that fire to move certainly that quickly due to air movement. Small gaps, what we've seen is under a ½ inch is really hard for that fire to propagate in those cavities. The rapidly depleting oxygen is going to starve that fire out. When we get up to around an inch, it might start, particularly if there's combustibles within those assemblies. And there's test assemblies that or test requirements like NFPA 285 that we need to kind of abide by for sure. But in these kind of 1-inch cavities, we oftentimes see the oxygen's depleted relatively quickly. But now when we get above 1 inch to the kind of the 2-inch plus, now we're introducing a lot more oxygen, right? And particularly if there's combustible materials, it's hard to kind of contain within this type of a chimney. And so while we like to see for increased moisture management wider gaps in ventilation and drainage, there is a point where from a fire perspective maybe it's not ideal to get bigger and bigger. All right, so the water resistant barrier, and this oftentimes serves as the inner layer of that rain screen. It's located inboard of that cavity. It serves as the secondary plane of water control behind the cladding. And so this can be done in a variety of ways. We'll talk about it on the next slide. It can be membranes that are lapped, but oftentimes it's part of a system that includes tapes and sealants. It can be part of the sheathings. It can be part of the insulation. There's lots of different ways that we can kind of manage water resistance within assemblies. And here's just some examples of that. I mean, just traditional building paper that's lapped at the joints, right? This is not necessarily serving as an air barrier, but it's serving as a shingled water resistant barrier. We see, standard polyolefins and sometimes, these house wraps that are taped. We've seen now sheathings, whether or not commercial or residentially, that can be water resistive on the face, but certainly you need to tape or seal up the penetrations in the joints. We see a lot of liquid applied products that also need to have kind of joints sealed as you're putting that up. Self-adhered vapor permeable membranes, right? So sometimes we want assemblies to be vapor permeable. It can be watertight, but vapor open. We can see that that sometimes we might want impermeable membranes, right? Depending on the assembly, we might not want vapor to migrate through it. And we'll talk about that in a little bit. Sometimes our water resistant barriers can be spray foam, which is also watertight if it's done effectively. Is another option if it's certainly meeting the code requirements. Exterior insulation, right? As we mentioned, this is a critical component in a lot of commercial rain screen assemblies for meeting specific code requirements around thermal performance. If we're introducing insulations into rain screen cavities, particularly open joint or perforated type claddings, these insulations must be moisture tolerant and self-supporting for that exterior wall. They must be, designed specifically to endure, what the environment has to offer. Again, when it comes to vapor migration and drying capacity of assemblies and walls based on the climates that we're building them in, insulations have vapor permeance levels, so we might need to recognize that and design the walls, particularly the moisture control strategies based on the vapor permeance of not just the membranes, but the insulation as well. Materials are properties are really critical. I mentioned NFPA 285 is a test assembly for the use of combustible products and non-combustible construction. And so understanding with insulation what the combustion and the smoke kind of impact are of those materials is really critical. And so what we see on rain screens, when it comes to exterior insulation, mineral wool is certainly one, XPS, EPS, we see polyisocyanurate, can be foil faced. We also see closed cell spray foam. Those are some of the most common type products that we'll see in rain screen. And so, another thing to think about here is, exterior insulation does play a role in water control, not just in terms of managing the vapor, but it serves as another drainage plane. When we look at a wall here on the left, maybe in a region that doesn't require exterior insulation, particularly in open joint type cladding, we're putting UV and moisture directly on the secondary line of defense or water resistant barrier, and really putting the onus on the installer to do an amazing job with that WRB to kind of keep it effective. On the right, now we've added exterior insulation, which we can see, is adding another line of defense and keeping the moisture off that water resistant barrier, right? We want to understand, again, the moisture tolerance of those materials, but it does help, offering another level of redundancy and moisture control. And so as we consider that and we look at these two assemblies, the one on the left, not having a continuous insulation layer, and we can assume, if moisture hits that polyolefin or that house wrap's got to be done pretty well. When we look at this assembly on the right, looking up the wall, if that moisture gets behind the cladding, it's got a robust amount of insulation in there that, that amount of moisture will have a long way to go to get to that water resistant barrier, right? And so when I've mentioned redundancy quite a bit, and when we think back to that kind of perfect barrier wall assembly, where again, we have to build perfect, whether or not it's a curtain wall system, structural glazing, insulated metal panels, right? We're relying on those sealants to work really well over time. But when we look at this, now we see 4 different locations of drainage planes, right? We see the face of the cladding, we see the back of the cladding, we see the face of the insulation, and then we see the water resistant barrier, right? So lots of different lines of defense. All right, so where do we put the WRB if we're using exterior insulation? And that can vary depending on the design and the types of products that we're using. Again, we want to see, and we would prefer to see, moisture tolerant exterior insulation. And if that's the case, the water resistant barrier is going to be at that backup wall location, right? As I've shown in the prior slides. There are materials out there, or if an installation is misspecified for sure and put on the outside of a building, or if we're looking at, moisture sensitive materials like cellulose or some of the timber type products that might have, less integrity around moisture, it might make sense to put a water resistant barrier outboard of the insulation, right? And install it in a watertight manner that protects, both the insulation and the structure from that moisture. If we're using foam plastic or, rigid foam, we have a couple of options here, right? We can design that rigid foam, which is typically vapor tight and airtight, to be an air and vapor control layer, and as well as a water control layer. So we can tape the seams and make that water resistant barrier outward of the insulation. But if we're not designing it that way, then, in many senses, we're going to put that water resistant barrier behind the rigid foam, which is what we see in this assembly. And then this last kind of image shows, again, if we were to use that rigid foam as the water resistant barrier, the air barrier, and possibly the vapor control layer, then we're taping those seams, and that water control layer is the outer face of our insulation layer. So again, these things can vary, again, based on the design and what we're looking to achieve. All right, so open joint claddings, or in scenarios where we want to protect the insulation, there's different ways to do it, but we do want to think about vapor control as well as UV control within these assemblies. You can see that there are, sometimes you're just putting a black membrane out front for aesthetics. Maybe you don't want to see the insulation behind the open joint. So, but we do want to think about the UV stability of those products. And then we want to think, how are we going to attach this? Where are we going to attach this membrane? It can be at the back of the cavity, at that face of the insulation, right? So you can drape these products over the insulation if that's what you choose. You do want to think about the vapor permeance of these membranes, particularly, again, if you're looking to optimize outward vapor drive and condensation control within the assemblies, and those products should be somewhat vapor open. You can install them either behind the hat channels, or in some cases we see them installed over the hat channels, which you see here on the right, maybe on top of the furring strips. Again, protecting those furring strips, or maybe the existing membranes that are not UV stable from any of the UV that's coming in those open joints. All right. We mentioned cladding attachments. So there's some assemblies that don't use exterior insulation. The cladding is attached, either to hat channels or through drainage membranes directly back to the structure. But if we're moving to these kind of robust systems that are using continuous insulation, now we got to think about, again, how are we extending the cladding off the wall? How are we, making sure that we're getting our insulation fitting in there? And how do we make sure that we're not losing the thermal efficacy of that insulation by introducing a tremendous amount of thermal bridging? And so, we can use continuous metal girt systems. We see these Z-girts quite often, either running vertically or horizontally, or sometimes in a crossing pattern. But we want to recognize is that any of these kind of continuous metals going through a thermal layer often result in very poor effective thermal performance. So we might have products that, insulation products that are R4, R5, R6, sometimes R7 per inch. But if you're putting metal framing, through them every few feet, that can reduce the thermal performance, 60, 70, 70%, right? So you're losing a tremendous amount of that thermal performance. So we have seen an uptick in kind of low conductivity, let's say fiberglass girts, as a result, to improve that thermal performance. Fiberglass girts don't transfer that heat energy or that cold energy across those girts like a metal or an aluminum does, right? They're kind of a thermally broken way to attach that cladding. But we don't have to just do fiberglass, right? Just minimizing that metal, kind of reducing those extensions for the Rainscreen system to clips, periodic clips, can really have a magnitude of improvement. So you can see just different examples of what that looks like. There's been some studies done on kind of